Hello and welcome to today's lecture on finite state machines. Here is the outline of today's talk. I shall give a brief introduction about what is finite state machine, why it is required, then discuss a finite state machine model. Particularly this is important in the context of implementation. Then I shall talk about two different types of finite state machines, Mealy and Moore machines. Then I shall discuss finite state machine design steps. Through a number of design steps, the specification is transformed into implementation in terms of gates and flip flops, and how that is being done I shall discuss in detail. Then I shall discuss realization of finite state machine using read only memory. As you know, read only memory can be used to realize combinational circuit. Similarly, we shall use programmable logic array for the realization of finite state machine. I shall discuss about them. Then I shall conclude my lecture with some concluding talks, concluding remarks. Any digital system will have some control part. Why digital system? Every system will have two parts, hard and soft, like hardware and software, body and soul. Similarly, any system, any digital system will have two parts. One is known as data path and the second is known as control path. For example, say data path and control path. For example, let me take off the example of general purpose computer, say CPU, central processing unit. As you know, it consists of arithmetic and logic unit, a set of registers, and these ALU and registers are controlled with the help of a control unit. Then the whole thing is known as central processing unit, and of course, you will require some interface for connecting to the outside world, and that outside it communicates with the outside world through a bus known as system bus. As you know, it comprises of address lines, data lines and control lines, and this is that interface. Now, this control unit controls ALU and registers which is inside the CPU, and not only that, it controls what is connected to the CPU through this interface through the system bus. So, you can see here the control unit is performing the role of controller of all these components which are present inside the CPU and also which is connected to the CPU through external bus. And essentially control path is realized by the control unit and data path constitutes ALU, registers and other things. So, you can see you require a control part, and finite state machines are commonly used to realize control parts. So, how do you realize the control part? It can be realized with the help of the finite state machine. For example, this control unit of the CPU can be realized with the help of the finite state machine. And essentially FSM provides, the finite state machine provides an organized structure for capturing control sequences and operation. As you know, a controller controls certain things through a sequence of events, through a number of steps, and it will require several functional components. So, this is being nicely captured with the help of a finite state machine. And a finite state machine can be diagrammatically represented by a state transition diagram. Question naturally arises, how do you really represent a finite state machine? There are various ways of representing finite state machine. For example, the specification usually is usually given in terms of simple English language, or maybe with the help of some programming language C, or maybe with the help of some hardware description language like Verilog and so on. Whatever it may be, that can be transformed into a more elegant representation with the help of what is known as state transition diagram, and it nicely captures the functionality as well as the control sequences. And in a state transition diagram, we have a level node, I mean there are level nodes that represent states. A finite state machine, as the name specifies, it will have a finite number of states, and those are represented with the help of level nodes, usually circle, and level directed edges represent transition among the states. That means the finite state machine will go from one state to the another state. That transition is represented with the help of edges, and on the edges you will specify on what condition the transition is taking place and what is the outcome of that particular transition. Let us consider a simple example to crystallize the idea. Consider a sequence detector that produces 1 when 5 ones appear sequentially at the input. That means, you are designing a sequence detector. That means, a series of inputs are coming, series of ones and zeros, that whenever there are 5 consecutive ones, you want to produce 1. That is the function of the controller. And let us see how the state transition diagram captures the functionality and the transition sequences. As you can see, the finite state machine of this sequence detector that produces 1 when 5 ones appear sequentially at the input can be represented with the help of 5 states S1, S2, S3, S4 and S5. And S1 we may call it as the initial state. So, if a 0 comes, it will remain in that state. That means, that here actually that 0/0 represents the first one is the input and the second one is the output. So, input and output for that transition is specified on the by the side of this edge. So, whenever the machine is in state S1, if a 0 comes, it will remain in S1 and 0 will be the output. Then if a 1 comes, it will go from S1 to S2, but still it will produce 0. So, again if however, whenever it is in S2, if 0 comes, again it will come back to S1 by outputting 0, but if a 1 comes, it will go to state S3 by producing 0, and then when it is in S3, it will again produce output 0 both for input 0 and input 1. However, when the input is 0, it will go back to state S1, and when the input is 1, it will go to state S4, and if another 1 comes, it will go from S4 to S5, still producing 0 because not yet 5 ones has occurred in the sequence, and if 0 comes, again it goes back to state S1. Finally, whenever it is in S5, if a 1 comes, we have already completed 5 ones 1, 2, 3, 4 and 5. So, 5 ones have come again. So, it will go back to state S1 and producing 1, or it will go back to S1 if the input is 0 producing 0. That means, in that case you have got only 4 ones at the input, not 5 ones. So, this is how the function of the sequence detector, which detects a 1 whenever there are 5 consecutive ones, can be diagrammatically represented with the help of a state transition diagram. So, this is shown with the help of this example. Now, comes the question of realization. This realization is related, I mean can be represented with the help of a generalized model. You can see this is the generalized model for finite state machine realization. It can be represented by 5 tuple. Pi is a set of inputs, it will have set of primary inputs x1, x2 up to n primary inputs. It will have a set of outputs Z1, Z2 up to Zm. So, M primary outputs Z1, Z2, Zm, which are produced with the help of this combinational logic circuit. And in addition to that, it will have a set of states which are represented by a set of flip flops. Here I have written D flip flops, but it is not really necessary to use D flip flops. You can use any type of flip flop, SR flip flop, JK flip flop. Only thing that excitation function for these flip flops will be different, but D flop is the most commonly used and the simplest. And so, the states are represented with the help of these flip flops, and so the states are, there are p states mentioned here, S1, S2 up to SP. So, if there are p states, the number of flip flops required will be root p, or sorry, 2 to the power k, that means you have got k flip flops, will be equal to p. And delta, the state transition function S plus is represented by delta S x, that means the next state is dependent on the present input x 1 to x n, this input combination, and the past history which is represented by the state of the machine. That means, it is a function of state and the present input. Similarly, output transition function, whatever output it will produce here Z, capital Z is essentially combination of Z1 to Zm. That is a function of again states, as you can see, the present state and the primary inputs. So, this is the generalized model. However, there are two classes of machines which are known as Mealy and Moore machines. So, Mealy machine, in case of Mealy machine, outputs are dependent on inputs and current state. That means, Z is equal to lambda Sx, as it is represented with the help of this diagram. Here, as you can see, the primary output is a function of both the primary input as well as the present state S. So, it is a function of both, and which is, that is why it is known as Mealy machine. On the other hand, the Moore machine, where the output is dependent, outputs are dependent only on current state, not on the x. Here there is a mistake. So, actually for Moore machine, if it is a Moore machine, then your Z will be equal to lambda into S, not x. It will not depend on input, it will depend solely on the state. That means, in case of a Moore machine, output is dependent only on the present state, not on the input. Okay. So, if there are n states, we have seen there are p states. So, p states means p different outputs are possible in case of a Moore machine. We shall illustrate with example. As you can see here, the output is dependent only on the present state Ps, not on the primary input. However, the next state function for both the machines is dependent on the primary inputs as well as on the present state, both here as well as here, both for Mealy and Moore machine. Now, let me give an example to crystallize the idea of Mealy machine. Here the state transition diagram of a sequence detector that produces 1 for each occurrence of an input sequence 0, 1, 1, 0 is shown here. In this particular case, again it is a sequence detector, because sequence detector forms the simplest examples of controllers. And here, as you can see, the finite state machine has 4 states, S1, S2, S3 and S4, and S1 is the initial state. Again, as you can see, whenever it is in state S1, if a 0 comes, it remains in 0 in this state S1. Then if a 1 comes, it goes to state S2 by producing 0. However, if a 0 comes, it comes back to state S1. Again, if a 0 another 1 comes, it goes to state S3 by producing 0. whenever it is in S3, it comes back to state S1 by producing 1, because here you can see it has fulfilled the requirement of producing 1. 0 it was when it was here 0 1 1 0, that is our specification. It should produce 1 when the input sequence is 0 1 1 0. However, instead of this, if it produces say 3 ones successively, so in that case it goes from S3 to S4 by producing 0, and if it continues to receive ones after that, it remains in state 4 as long as ones are inputted. However, as soon as a 0 comes, it goes back to state S1. So, this is the specification of a finite state machine that realizes the sequence detector for the input sequence 0 1 1 0. Okay. So, this is the machine. Now, let us consider a Moore machine. The state transition diagram of a sequence detector, again I have taken up the example of sequence detector that produces a 1 if the sequence consists of even number of ones or even number of zeros. That means, suppose you have inputted a sequence of zeros and ones and you have finished the input sequence, and at the end if the number of ones and number of zeros both are even, then it produces a 1. On the other hand, if the input sequence has got odd number of 0 or odd number of 1 or odd number of zeros and ones, then it produces 0. That is the functionality to be realized, and this can be represented with the help of this state transition diagram. It has got again 4 states, starting with state S1 where both are 0, there is no input, I mean assuming that both the ones and zeros are 0. So, in this case even means 0 0, or it can be initially it is definitely 0 0. So, it is in state 1, and then from here it will go to whenever a 0 comes, it will go to OE odd 0 even 1, and if a 0 comes, again it comes back to S1, because it has now got even number of zeros. So, it produces a 1 if that is the end. However, in this way it goes from S1 to S3, S2 if a 1 comes, and it is here you can see it is even and odd. Odd means number of ones is now odd. If another one comes, then the number of ones become even, then again it goes back to this S1 state S1 where it produces a 1. Similarly, it is in state S3 when both are odd, that occurs whenever if it starts with 0 1 0 and another 1. So, it goes to state S3, but again if whenever it is in S3, if a 1 comes, it goes back to odd even, that means the number of ones become even 1 and 1. Similarly, it goes back to if a 0 comes, it goes back to state S2. So, this is how state transition occurs, and at the end it may have a number of zeros and ones like this. Say for example, say suppose the number of inputs are 6. So, it may have 0 0 1 0 1 0, let us assume this is the sequence. So, here you can find the number of zeros is 4. So, it is even, and number of ones is 2. So, it is also even. So, that means it will produce 1. On the other hand, if the input sequence is 0 1 1 0 1 0, then the number of ones is odd, I mean 0 is odd and 1 is also odd. So, then it will produce 0. So, that means here it is OO, state is OO, so it will produce 0. So, in this case, as you can see, depending on whether the final state is even odd even odd or odd odd, it will produce 1 or 0. Only when the final state is even and even, both the number of zeros and number of ones are even, then it produces 1. So, this is the example of a Moore machine. Now, coming to the finite state machine design steps, how do you proceed? So, normally the specification may be given in terms of, as I said, simple English text, or it can be specified with the help of a program, C program, or we may specify it nowadays with the help of some hardware description language like Verilog or VHDL. So, whatever it may be, from that you may create a state transition diagram which I have already shown. Now, why you are actually realizing state transition diagram? Because the state transition diagram captures the state machine functionality and the different transitions very nicely. Whenever you create the state transition diagram, you have to do some simple checks. You have to ensure that all states including the ideal state are captured. Number 2 is you have to check that transitions for all possible input combinations are leaving each of these states. For example, in this case, in this particular example, there is only one input. So, the number of possible input combinations are 0 or 1. So, from each state 2 edges will emerge, one is 0 for 0, another is for 1. Similarly, if there are 2 inputs, then there will be 4 possible outputs 0 0 0 1 1 0 1 1. So, that you have to check that, so that all possible transitions are captured by that state transition function. Then okay. Then insert appropriate output to each transition. So, you have to provide a necessary output based on the behavior that is given in the form of English text or whatever it may be. You have to capture the, you have to insert the appropriate output, as I have already shown, that is necessary in the context of Mealy machine. However, in the case of Moore machine, the outputs are specified as part of the circle of the state, within the circle of the state. And then insert loops into any state when with appropriate conditions for remaining in that state. As I have shown, there are self loops, these loops, this type of loops, whenever continuous sequence of zeros comes or continuous sequences of 1 comes, you have to give this kind of loops. So, this is how you will create the state transition diagram, that is the step 1. Step 2 is state minimization and reduction. This plays a very important role, because reduced number of states leads to simpler finite state machines. What may happen, you may end up with a finite state machine with more number of states than actually required. So, there will be redundancy, and that redundancy is not desirable from the viewpoint of implementation, because more the number of states, more hardware you will require to implement it. So, one important step is state minimization, and how it is being done. Actually, 2 states of a finite state machine are equivalent if and only if for any input they have identical outputs and the corresponding next states are also equivalent. So, what you have to do, you have to identify the set of equivalent states, and then only one of the equivalent states will be present in the final state transition diagram. So, it is an important minimization step, and there is a systematic technique, systematic procedure to identify and combine states having equivalent behavior. We are not going into the details how state minimization and reduction can be done, but this is available in any textbook on say switching circuits and logic design, including the book which I have studied in my student days, the book by G. Kohavi. So, I am not going into the details of state minimization and reduction. Let us now consider another step, that is finite state encoding. What do you really mean by encoding? You see, suppose a machine has got p states, as I have already told, general finite state machine. We represent it by symbolic names S1, S2, S3 up to SP, but you have to realize the machine. So, each state has to be given a binary code. Just the symbolic name is not enough. So, that is being done in this important step known as finite state encoding, finite state machine state encoding. So, in the state assignment state, each state is given a unique code. So, all the I mean each state will be given a code and that should be unique. So, that it does not, I mean there should not be a common code for two states. And why state assignment or in state encoding? Actually there are it is sometimes called state encoding, sometimes it is called state assignment, both are same thing. So, state assignment strongly influences the complexity of the combinational logic part. So, depending on what state assignment you do, it influences the the hardware, that means realization of the finite state machine, that means area required by the machine, by the combinational part, or the delay of that circuit, and later on we shall see it will even influences the power dissipations. That is where we have the scope for minimizing power, later on we shall discuss about it. So, traditionally state assignment has been used to optimize the area and delay, as I have already told, and recently this is being also used to minimize the power dissipation. And for the example that I mentioned in the beginning, that means it detects there are detects 5 ones in a sequence. For that machine, the state assignment is shown here. It has got 5 states S1, S2, S3, S4 and S5, and you can see the codes I have just given serially. That means S1 is given the code 000, S2 is given the code 001, S3 is given the code 010, S4 is given the code 011, S5 is given the code 100. Since there are 5 states, you will require 3 bits. That means with the help of 3 bits, you can represent up to 8 states. So, as long as the number of states is 2, only 1 bit is sufficient. If the number of states is within 4, 2 bits are sufficient, so on. That means, if k, you will require k bits to have 2 to the power you will require if you have got k bits, then the total number of states, maximum number of states will be equal to p, where p is equal to 2 to the power k. So, this is the second step, and after that step you will start the fourth, I mean there will be fourth state known as state table formation. So, here you can see we have the 5 states S1, S2, S3, S4 and S5, and the corresponding states are given here S1, the codes for the different states, and the corresponding state variables are y3, y2 and y1. So, these are the state variables y3, y2 and y1, and the corresponding codes are 000, 001, 010, 011 and 100. Now, you can easily form a table from this state transition diagram known as state table. So, this step is known as state table formation. How are you doing it? You can see, suppose this is machine is in state S1, this is the present state, and if the input is 0, x1 is 0, then what it does? It remains in state S1 as it is shown 000 is the state S1, and also it produces 0. So, you enter 0 here. Similarly, when a 1 comes, if the input is 1, as you can see here, if it is input is 1, it goes to state S1 and the corresponding code is 001 and output is also 0 as it is listed here 0. So, in this way you can complete the entire table. For example, if it is in S3, it goes to S4. So, S3 is it goes to S4, it goes to S4 when the input is 1. Input is 1. So, the corresponding code is 011 for code, the code for S4 is 011 as you can see, but however, the output is 0. So, finally, as you can see, when the machine is in state 5, it goes to state S1 when the input is 0 by producing 0. So, 0 0. So, here you can see there are 2 entries. So, 0 0 0 S0 it goes to state S1 and producing output 0, or it goes to state S0 by producing 1. So, both are shown here. So, that means when the input is 1, it produces 1 going to state S1. So, you can see this table is very useful, and this table is somewhat similar to truth table. And as you are all familiar with realization of Boolean function from the truth table. So, once you have a truth table representation, you can very easily realize different functions. What functions you will realize? You will realize the next state functions and the output functions. These are the we already know the general representation of a finite state machine. We have a set of outputs, primary outputs, and also you have to generate the output for the next states. So, next states and outputs are realized with the help of combinational circuit, and obviously this will form our next step, implementation. So, here what you are doing, you can implement the finite state machine with the help of some circuit, that means the combinational logic part you will realize with the help of a circuit. So, there are several alternatives in this case. The combinational logic, as you know, can be realized in a number of ways. What are the different ways? Let me list out. Number 1 is realization of the combinational circuit part. Number 1 is you can realize by using either 2 level or multi-level realization using gates, discrete gates like NAND, NOR, inverter. So, we have already discussed how you can realize functions by using this type of using this NAND or an inverter. In this particular case, from this truth table that I have shown, that means the truth table of the finite state machine or state table of the finite state machine, usually for a combinational circuit we call it truth table, and for a sequential circuit we call it state table. So, usually they actually represent the same thing. So, in case of state table, for this state table you have to realize y3, y2, y1 and z. So, these are the 4 Boolean functions you have to realize, and here the inputs are lowercase y3, lowercase y2, lowercase y1. On the other hand, you are realizing uppercase y3, uppercase y2, uppercase y1 and z. So, this y3, y2, y1 and z in this particular case are functions of small y3, small y2, small y1 and x. And so, it is essentially a 4 input, 4 output realization. You have got 4 binary inputs and you will produce 4 binary outputs, and the functions that you have to realize is given here. For example, z is equal to y3, y2 bar, y1 bar x, and y3, capital Y3 is equal to y3 bar, y2, y1 x, and y2 is equal to y3 bar, y2 bar, y1 x plus y3 bar, y2, y1 x, y1 bar x, and y1 is equal to y3 bar, y2 y2 y1 bar x plus y3 bar, y2 bar, y1 bar x. And here you can do a little bit of minimization. you cannot, then the other functions cannot be minimized, but this can be minimized. So, you get y 3 combining these two, you get y 3 bar. This y 2 will vanish, because here you have got y 2 and here is it is y 2 bar. So, it will be y 1 bar x. So, this is how you can realize the Boolean function y 1, capital Y 1. So, once you have got these Boolean expressions, you can realize with the help of NAND, NOR and inverter. As you know, this can be realized by a single NOR gate. So, how it will realize? You can say Z will realize by a NOR gate. There are 4 inputs. What will be the inputs? As you know, the complement of the network forms the from the NMOS part. So, here it will be here the inputs will be y 3 bar. So, you will require a inverter y 3 bar, then y 2, then y 1 and x bar. So, this will represent Z. They realize Z in terms of gates. So, it has been realized with the help of NAND, NOR and inverter, as you can see. So, this realization is done using NAND, NOR and inverter. Similarly, you can realize y 3 will be can be realized in this way. Again you will realize y 3 with the help of a NOR gate, and in this case you will require y 3, then y 2 bar, then you will require y 1 bar, and you will require x 1 bar, sorry x bar. So, you will require an inverter. So, this is how you will require realize y 3. On the other hand, y 2 can be realized by using because you require 2 level gates that you can do, and you can realize this by using a simple NOR gate. So, here you will require y 3, y 1 and inverter, and this will require 2 more levels, that means NOR at the final gate and another NOR in the initial gate. So, you will require 2 levels of NOR and NOR. So, this is given as an exercise to you, you can try it out. So, this is how you can realize functions by using NAND, NOR gates, but that is not the only way by which you can realize functions. You can realize by using ROM, read only memory. Sometimes you have to realize very complex circuit. So, in that case the number of inputs and number of outputs can be quite large. So, realization of the combinational circuit by using read only memory is shown here. I have already explained that ROM can be used to realize combinational circuit, and here it is shown how it is being done. So, this x, y 3, y 2 and y 1, these are given as inputs to the ROM, and it produces the output z, y 3, y 2 and y 1. How it does? You can see the structure of the ROM is given here, read only memory is given here. As you know, ROM is nothing but it consists of a decoder and an encoder. Decoder function, as you know, it will produce 16 outputs for 4 inputs, because it is a decoder, and for any input combination the output will be 1. So, it produces a 1 here on the bottom line if all the inputs are 0, and it produces a 1 on the top line if all the inputs are 1, and for all other input combinations it will produce one of the remaining lines, and that is the function of a decoder. Now, what will be present in the encoder part? I have already discussed about the realization of encoder part by using MOS transistors. So, that means wherever there is a 1, I mean that particular point is there, you will you will have a transistor. In all other places transistors are not present. So, we have seen there are 5 terms 1, 2, 3, 4, 6 terms. So, as you have already seen in the function 1, 2, 3, 4, 5, 5 terms are there. Actually this has to be expanded into 2. So, there are 6 terms, because this capital Y1 I have combined 2 min terms to get this minimized form. So, essentially it has got 6 min terms to realize the functions, and those 6 min terms are shown here with the help of 6 dots. That means, whenever that particular input combination is 1, for example, in this case it is y3 bar, y2 bar and y1 bar and x, this is 1, this particular y1 is 1. So, y1 is 1, we have seen y1 is 1 when y3 bar, y2 bar, y1 bar, y2 bar and x. So, that realizes here. However, when this is 1, this line will be grounded. So, instead of 1 it will produce 0. So, that is why you will require an inverter to really produce y1. So, you can see we have put an inverter at the output, so that it produces a 1 instead of 0. So, this is how you can use several most, I mean by this is the implementation by using mask programmable ROM. That means, at the time of fabrication the mask is fabricated, the ROM is fabricated in the mask stage. That means, the fabrication house does it. There are other alternatives I have already discussed, where you can have, instead of this type of mask programmable ROM, you can have electrically erasable ROM. In that case, each particular node point will have a floating gate transistor, and that floating gate transistors can be programmed with the help of different techniques, which I have elaborated in detail in my earlier lectures. So, let us not go into the details of that, but the basic idea is you can realize this ROM function either by using mask programmable ROM, or you can do it by using electrically erasable ROM, or you can do it erasable programmable ROM, or you can have those flash memory. So, in that case also you will use those floating gates. So, I am not going into the details of that, but this is one very interesting and useful way of realizing the finite state machine. So, whenever you realize a finite state machine with the help of a ROM, one very important point you will notice that use of ROMs to realize Boolean function is wasteful in many situations. Why it is wasteful? Actually, when the number of input variables is very large, then total number of combinations is very large. Say there are 10 input variables, I mean total number of inputs is 10, including the state function, state variables and the input variables. So, it will require 2 to the power 10 different combinations. So, out of those 2 to the power 10 combinations, usually a very small fraction is used to realize the function. That means, output is 1 only for a very small fraction of the total possible combinations. For example, in this case out of 16 different combinations, only 6 are required to produce the outputs Z, Y3, Y1, Y2 and Y3. So, that means 10 different combinations, you can see that there is no dot. So, for 10 different combinations there is no dots, that means they are not required to realize these functions Z, Y1, Y2 and Y3. However, you have to realize, I mean they will be generated by this decoder circuit, and unnecessarily you have made the decoder complicated to realize those outputs, to get those outputs. So, that is why I am calling it wasteful. Is there any way by which you can reduce this waste or minimize this waste? Actually, another technique is there to realize a combinational circuit, that is done with the help of what is known as programmable logic array, PLA. What is PLA? So, in PLA what has been done, we have seen a ROM comprises two parts, decoder. If you have got n inputs, it will produce 2 to the power n outputs, and then there is a encoder. This encoder part is programmable, you can program it to produce different outputs. So, here decoder is not programmable, encoder is programmable, you can say programmable. Now, instead of this, if we do it in a, if we incorporate little more programmability, what we can do, we can make the decoder programmable. That means we can apply the inputs, then we can have instead of decoder we can have two levels, and it will produce only the desired outputs, say 6. So, it will produce 6 outputs, and which will go to the encoder. So, this is the encoder, but the decoder is done programmable. So, this is the programmable decoder, you can say. This one is programmable decoder. Only the desired combinations for which you require output 1 are generated here, not the redundant or unnecessary products. So, and then of course, it will produce the necessary outputs. So, that is the basic philosophy behind the programmable logic array, and there are several structures. The most common one is the this AND OR realization. Here since you will require both complemented and uncomplemented outputs. So, each input is complemented and those outputs are fed to a stage known as AND plane, as if you are doing AND OR realization. So, you are realizing this in this form, say x1, x2, x1 bar, x2, x1. So, AND and OR. So, this is realizing the AND operation and this will performing the OR operation. However, after performing this AND and OR, it may not produce F1, it may produce F1 bar, because you will be realizing not by using AND OR logic, but by using NOR structures. So, since you will be realizing by NOR in this manner, so this is one NOR. So, you can see F1 is equal to x1 x2 plus x1 bar x2 x3, that can be realized in this form. So, this is a NOR, x1 bar bar plus x2 bar. This can be realized by a NOR function, this can be also realized by a NOR function, and then final NOR will realize the other function, and which can be complemented to get F1. So, you can see F1 is realized here. So, to get F1 you have to use a inverter. So, this is the basic structure of the most common type of PLA, and PLAs, as you can see, it is not producing unnecessary outputs. So, 4 outputs are required to realize F1, F2, F3, 4 combinations or product terms are required to produce to realize those functions. So, only those 4 are generated by this stage. So, you have made the decoder part programmable with the help of this AND plane, and then this OR plane is somewhat performing the function of that encoder of that ROM, and you are getting the necessary outputs, and of course, you will require inverter and you can get the functions. So, the realization of the functions that you have already done in terms of transistors I have shown here. So, you can see this is this part, these are the 4 inputs x, y1, y2 and y3. These are the 4 inputs lowercase y2, y3, y2 and y1 and x, and you have got inverters which are applied to get, this is the NOR, 4 NOR function, 5 NOR function 1, 2, 3, 4, 5. We have seen there are 5 product terms. So, 5 NOR functions are generated, and these 5 transistors are essentially those pseudo NMOS loads. So, this is the pseudo NMOS implementation. So, these are the loads, those pull up transistors, and these are the pull down NMOS transistors for realizing different functions, different end plane functions. And then the OR operation is performed by another NOR structure which is shown here, and these are the loads, the pull up devices of that NOR functions, those pseudo NMOS gates, and you can see these are the NMOS transistors. You require only 5 transistors here, 1, 2, 3, 4, 5 to realize Y3, Y2, Y1 and X, Z. So, you see this is the detailed PLA realization in terms of transistors. So, that basic structure that I have shown, I have elaborated it with the help of transistor, this part, this end plane and OR plane, how it is realized by using MOS transistors is shown here. This is for the that 5 consecutive 1 sequence detector realization is shown here. So, with this we shall come to the end of today's lecture with these concluding remarks. First one is, finite state machines constitute an integral part of digital systems. As I have told, for any digital system you will require data path and control path, and control path can be realized using finite state machines. So, they will form an integral part of the digital system. Second is, as I have told, there are 2 basic type of FSM models known as Mealy and Moore machines. I have introduced these 2 models because any realization will use one of the 2 models, either the Moore machine or the Mealy machine. So, whenever it is a Moore machine, if the output is dependent on only on the states, then it will be a Moore machine. On the other hand, if the outputs are dependent on both inputs and states, then it will be a Mealy machine. And we have discussed how the specification of the function of a finite state machine can be transformed through a number of steps to actual implementation using gates and flip flops, or even in terms of transistors, as I have already explained, and various implementation steps have been illustrated with a running example. Now, finite state machines, I have given example of only sequence detector. You may have the impression possibly finite state machines are used only to realize sequence detector. That is not true. It can be used to realize any controller. For example, counter. Counter is a kind of finite state machine where without primary inputs. Similarly, you can have shift register, ring counter, or you may nowadays you will be finding vending machines in railway station, airports, even in IIT campus you will find vending machines. The controller of the vending machines can be realized, say coffee vending machine or say newspaper vending machine can be realized with the help of these finite state machines, or you can use realize traffic light controller. So, these can be realized in a similar manner, and I have discussed everything by manual implementation, but when the machine is very complex, for example, you are realizing the control unit of a 32-bit microprocessor. In that case, manual design is not feasible. So, you have to use automated technique to realize a finite state machine, and fortunately automated tools and techniques are available. And later on we shall see low power FSM implementation technique, that I shall discuss later, and for the time being, thank you.